All right, guys, we are starting section 5.4 in our functions and relations chapter here. And our lesson opener, let's think about each of these things. Determine whether each distance described increases or decreases. So if we're talking about the distance from school as you drive from home to school, is that distance increasing or decreasing? Well, here's you. Here's school. As you drive to school, what's happening to the distance between you and school? You're getting closer and closer to school, so therefore the distance decreases. What about the distance from school as you drive home? Well, as you drive home, the distance increases. What about the total distance traveled as you drive from home to school? Well, when I drove to school this morning, I drove 2.2 miles. And when I drove back home, I didn't erase those 2.2 miles. I had to drive another 2.2 miles. So what happened to my distance? If I started at 0, what happened to my total distance traveled? My total distance traveled actually increases. If you think about total distance traveled like the odometer in your car, no matter whether you drive forward or backward, anytime that you drive, your total distance traveled is going to increase. Would this increase or decrease? Would a girl's heart rate increase or decrease if she changes from walking to jogging? Her heart rate's going to go up, so that's an increase. What about when she stops jogging and rests on a bench? That would decrease. All right, before we move on, let's go back to these events, and I want to think about how we could represent this graphically. So let's come back here to our very first question. Okay, and think about how could we represent this graphically. Okay, if this represents the amount of time, and this represents our distance from school, our distance is going to decrease. So maybe I start out here. At the beginning of my trip, I'm far away, and the more I drive, the closer I get to school, right? My distance decreases. What would the graph look like as I drive from school back to home? Again, if this is time and this is distance, okay, I'm leaving school, so I'm right at the school. My distance is 0, and the more I drive, the farther away I get from school, my distance increases. What about this graph of the girl with the heart rate? Okay, so she changes from walking to jogging, and then she goes from jogging to rest on a bench. So let's say she's walking, her heart rate's pretty steady, and then she starts to jog, so her heart rate increases, right? And then she stops jogging, so maybe she sits and rests on a bench for a while, her heart rate's steady. If she sits long enough, her heart rate will start to drop slowly again back to where she started. So we could represent that information graphically by drawing something that looks like this. Our biblical correlation comes from Hebrews. We've seen it already so far this unit. So let's just remind ourselves that we are to be confident in Christ and confident in our salvation. And our goal for you as a student is to be a confident student, to be confident in your learning and the skills that you are gaining. Our lesson objective for today is that you, the student, will draw and interpret graphs representing real-world relationships. Now, there are more slides in here that we are going to do. So when I start skipping slides, don't freak out, okay? I'm only going to do certain ones of these slides. The rest of these you can just see in your book when you're ready to look at all the information. But for our purpose today, I'm just going to do just a few things. So in your book, on page 200, there is a chart a chart showing the relationship between the age of a largemouth bass and its length. Now, age is not affected by length, so age is going to be the independent variable on this axis, or independent variable, which is the x-axis, the horizontal axis, and length is dependent. The length depends on the age, and it goes on the vertical axis. The graph looks like this. So we've grabbed this data that's been given to us, that a largemouth bass at 0 years of age is 0 inches in length, and at 1 year of age, it's 6.5 inches in length, and at 2 years of age, it's 11 inches in length, and so forth and so on. And we can use this information to answer some questions like, at 1.5 years old, what is the average length of a largemouth bass? At 1.5, we go up, The average length is right here at 9 inches. Or what's the average length of a bass at 3.5 years old? And we go up to the graph here and we can see it's 15 inches. Or we might ask, around what age does a largemouth bass reach 18 inches? Well, if we follow 18 inches, then we can see that it reaches 18 inches near 8 years of age. So we can use this information to show real life data. We can also use it to make predictions. Let's say I decided to buy a pet largemouth bass, and I needed to know how big of a tank to get. And my largemouth bass is only 2 years old, and maybe I don't want to buy a huge tank right now. And I might think, well, in the next 2 years, how much is it going to grow? Well, in 2 years, it's only going to go from 11 inches to 16 inches. So I need to make sure I get a tank big enough to fit that growth. So we can use it to make decisions or even make predictions. This is called mathematical modeling. Mathematical modeling is just the process of graphing data to study the shape of its distribution, to make predictions, to see relationships, and to see patterns. You've got some other mathematical modeling examples in your book. Page 201, you can look at the stamp costs. We're going to skip that one. And on page 202, you can see that there is a skydiving example. So let's answer some questions about this particular graph. On the bottom, our independent variable is the time, and our dependent variable is the distance. Distance changes with time. Time does not change with distance. We can use this graph to answer this question. How far has the skydiver fallen after 10 seconds? Well, on our graph, if we go along the 10 seconds on the bottom and go up to where we meet the actual function, we can see the skydiver has fallen slightly less than 1,500 feet, maybe closer to 1,300 feet. We can also see how long it takes the skydiver to fall 2,000 feet. And if we go 2,000 feet over to our graph here, and then when we hit that point, go straight down, we see it takes the skydiver almost 15 seconds, so maybe close to 13 or 14 seconds. It looks like there's a little hash mark there. I can't see it very well, but I think that's 14 seconds. Now, what if we were supposed to describe the first 5 seconds and the next 15 seconds of the fall? Well, you can see for the first 5 seconds, the skydiver went from 0 to 500. That's a change of 500 feet in those first 5 seconds. Okay, and then from 5 to 10, fell about, from 5 to 1,300, so that's 800 feet. And from 10 to 15, it's about another 800 feet. So the first 5 seconds, he only went 500. But after that, his distance per 5 seconds actually increased a little bit. What do you think happens at the top of the skydiver's dive? You'll see that his distance falling kind of slows down a little bit. Why do you think that might be? Write down your predictions and we can talk about that in class. However, this might give the answer away. Here is another model, and this model shows again the relationship not between time and distance of a skydiver, but time and speed. So we're starting at 0, 0. So this must be when the skydiver is in the plane. No time has passed. He's not going any speed. As soon as he jumps out of the plane, the clock starts. And what do you notice with his speed? The longer he's diving, the faster he's falling. His speed keeps on increasing. And then all of a sudden, he's still going fast, but his speed isn't increasing anymore. His speed is staying the same. Okay, there is a word for this in science. If you know that word, I'll ask you next class, and you can tell me what that word is. Okay, time passes. He's not going any faster. He's going fast. He's just not speeding up. And then all of a sudden, there's a very sharp decline in his speed. He was going fast, and now he has slowed way down, although he's still not back at 0. And we're going to gradually go a constant speed here for the rest of our time. All right, see if you can think of what might cause a skydiver to all of a sudden slow down very suddenly. And no, he did not hit the ground. If he hit the ground, his speed would be 0. So it's not hitting the ground that slowed him down. All right, that was a very quick lesson. Like I said, we weren't going to go over all these examples, but it should be fairly self-explanatory what we did. If you have any questions, you can look at the examples in your book or write down any questions you have for next class. Today we drew and interpreted graphs representing real-world relationships. That was our goal, and that's what we did. I'll see you guys in next class.